This video is for NMR Part 2. So this is about what goes behind the scene in the instrument. So we were looking at the protons, so a hydrogen atom. It has one proton in its nucleus, and this proton spins about an axis. And because of that circulating charge, it gives rise to magnetic fields. Now let's imagine this is the hydrogen that is from one of your samples from the previous video. So one of these H. So they will have their protons spinning this direction and this direction. And when you put this ethanol into the NMR instrument, there is an external magnetic field. This external magnetic field refers to the one that is from the NMR instrument. So now there's the magnetic moment from the proton itself and also from the instrument. Okay, so the spin, it will either spin in, okay, so this way or this way, so opposite direction of each other. One of it will align with the external field and the other one will be aligned against this external field. Each of them has a half unit. So before putting it into the NMR instrument, let's take one of these protons. When it's spin this way or this way, it's the same energy level. There's no field at that point. But when you put it into the instrument also has its magnetic field. And because of that, there is one direction that is aligned with that field and the other direction aligns against that field. So we have an energy difference here. This energy gap depends on two things. One is that instrument, so it's something you can set on your instrument. And the other thing is the proton environment. So meaning different protons at different environments, they're going to have different gap of energy. That's how we get that different sets of peaks. It's because they've got different energy gap. This is why when you have protons in the same environment, they will only give you one set of peak, one signal for that. Because they have the same environment, they will have the same energy gap. So just one set for them. And another set for a different environment here. And one more for this OH alone. That energy difference, E equals to HF, which is a formula you've seen before. Or E equals to HV for some syllabus. It's the same thing. V or F here means the frequency of the radiation. Okay, even though these protons, they're in the same molecule, we put them into the same NMR instrument. They've got the same constant external field. When we say external here, we mean the NMR instrument. So they all feel the same from the instrument, but they are different when they've got different environment. For example, what this proton experience compared to this proton, it's different because they've got different environment. This orange one has 3 neighbors and this yellow one has 2 neighbors, and they will affect each other because of the spin, the proton spin, which causes magnetic fields. So the proton spin explains why we have a certain sets of peaks. So there's 1 environment, 2 environment, 3 environment. We'll have 1 environment, 2 environment, and 3 environment. So 3 sets of peaks. But it doesn't explain why is it here, why is it here, and why is it here? Why is the chemical shift as such? So that can be explained by the electrons. So enough about the protons. Now let's discuss the electrons here. So this bond is an electron, right? What happens to the electrons? Electrons are paired, of course. 1, 2, and they spin in opposite direction. Okay, when placed in an external, again, they mention external field. So this external field, again, we're talking about the NMR instrument. Remember the proton spin just now, it aligns in such a way to be aligned with or against the NMR instrument. So these electrons, they will spin in such a way so that it can protect the one that is against the instrument. So it forms a shield to protect this proton. So the electrons will also spin and causes a certain magnetic field as well. So I'm going to use arrows to represent. It's just for imagination. So I'm going to use arrows to represent if it's going against each other. So if this is the direction of the proton spin, and this is the direction of the external field, which is from the NMR instrument. So it's going against each other. The electrons will spin in such a way that it will protect or shield the proton. So I'll draw it this way. Okay, do you see that in such a way, this electron spin so that it will protect this proton from this field by going the same way. So up is with up, down is with down. So it's sort of protected. So it shields the nearby protons. Okay, when something is shielded, in your spectrum, you'll see that it's closer to the TMS. So it has a smaller value. So that is when it's shielded. Okay, let's imagine the same thing again. So proton this way, NMR instrument this way, opposite direction. So it needs protection. The electrons will try to protect it, like just now. So up is with up, down is with down, but there's a problem now. If our proton is near an electronegative atom, this atom loves electrons. So imagine it such a way where it got pulled to the other side because it loves this oxygen. Oxygen loves electron. So when it spins, do you see that now it doesn't protect the proton? It's trying to spin to protect the proton, but it doesn't. Now down is with down and the proton is all alone. Up and the other up is on, is near to the electronegative atom. So this is not protected. This is not shielded. Okay, it's just for imagination. Not shielded means it's far away from the TMS. So you'll have a larger value, such as the other day when you see aldehyde, it has like 9 point something. So that's because of the CO from aldehyde, you'll get a higher value for that peak, that set of peak. A benzene ring is similar to that electronegative atom just now. It also de-shield or doesn't shield the proton from the NMR instrument. This is because of the delocalized pi electrons from the benzene ring. It creates a strong diamagnetism effect. So same as what we did for O just now. So we imagine the proton is at opposite direction. The magnetic field from external is the other direction. The electrons wants to protect it, so it's supposed to go like that, but no, it went in. So it becomes even more of a burden. So up with up, and the proton is all alone, so it's de-shielded. The protons which are shielded, their peaks will be closer to TMS, and protons which are de-shielded, their peaks will be further away from TMS. Now let's see how a neighbor will affect the occupant in this house. We'll use the house system again. So this is one house, this is the neighboring house. There's 3 occupants here and 2 occupants here. Let's focus on this occupant first, the 3 protons. Okay, what neighbors do they have? They've got 2 neighbors, let's say a husband and a wife. Let's say I have a friendly husband, friendly wife here, neighbors. So I have one pattern here. And I have friendly husband, mean wife, or mean husband, friendly wife. So these 2 would be something alike, one good neighbor and one not so good. So there's 2 of that pattern, so double the range here. And the last one, mean husband, mean wife. So I get one more. So that's how they affect, how the neighbors affect the occupants in a house. So that's 3 persons with 2 neighbors. That's 3 minus 1. So how will these 3 neighbors affect these 2 occupants here? There's 3 of them. So there's many patterns now. It could be a mother, a father, and a child. So it could be friendly, friendly, friendly. It could have been friendly, not friendly, friendly. It could be not friendly, friendly, friendly. So we could go on and write all of them and get this. Friendly, friendly, friendly. Friendly, friendly, not friendly. Friendly, mean, friendly. Mean, friendly, friendly. So there's 3 of them where there is 1 of them who's mean, and there's 3 patterns where 2 of them are mean, and there's 1 pattern where all of them are mean, and these 3 are friendly. So I've got 4 groups of pattern. Therefore, I'll get a quartet. 1, 2, 3, 4. So that's 2 occupants has 3 neighbors. How do I get 3? 4 minus 1. So if you have 1 neighbor, that's only 2 patterns. So you'll get a duplet. It will be 1:1. So they are the same height. But if you get 3 patterns like just now, so triplet, there will be 1 that's extra high. It's 1:2:1. You'll see the peak is something like that. And if you have a quartet, it will be 1:3:3:1. What do I mean 3? There's 3 patterns here. So 1 pattern is to 3 different patterns. So 3:1. So 1:3:3:1. So looking at the height of the peak, you can actually guess whether it's a quartet or a triplet. If you're ever in doubt, for example, this one, should I count this peak or not? So if you see these 2 same height, the ones that have same height should be like there's even number 4. It's a quartet. So this is probably a quartet, and this peak is not counted. Like for example, if I'm looking at this, should I say this is a quartet or a triplet? Should I count this peak or not? So look at the ratio here. An even number would have the same height peak. An odd number would have 1 that is extra high. So this one has 1 that is extra high. I would say this is a triplet and not a quartet. Okay, let's say we go into the lab. How do we do this in the lab? So take 20 milligrams of the sample that you want to test. So whatever organic compound that you don't know what's that, and you want to figure out what structure it has. Dissolve that in about 0.5 centimeter cubes of solvent, and this solvent must have no protons. Otherwise, the protons from the solvent will show in your spectrum, and you'll get messed up with your sample. So it's hard for you to solve what is the sample. Okay, so what kind of solvent have no protons? For example, CCl4 or CdCl3. Sometimes they use heavy water, but if they use heavy water, all your OH peak won't be there, and all your NH peak won't be there. Okay, a drop of tetramethylsilane, that's the TMS, that will give you your 0 peak or your controlled peak, your reference peak. Okay, so we saw what is tetramethylsilane. So we use TMS as a reference because it gives us a very strong singlet peak because of that 12 protons, and it doesn't interfere with our organic compound, the one that we want to solve. It's inert, so all these makes it a good reference. So that's why it's taken as our 0 peak. And then this sample tube will be suspended between the poles of the permanent magnet in our NMR instrument. This is a summary of the theory. So protons, this is a proton NMR. Protons possess nuclear spin, which generates magnetic moment, the moment aligned with or against external magnetic field, which gives 2 energy. Energy difference in the radio frequency range and the gap depends on the nature of the chemical environment. of the proton. And as for the one about electronegative atoms, electron pairs, they spin in opposite directions and shield nearby protons from external field which reduce frequency absorption. If a proton is near an electronegative atom, it is less shielded. So that's de-shielded, therefore has higher frequency. Okay, let's come back to the chemical shift for a while. Okay, if ever you see a structure where there's 2 oxygen atoms, you might want to suspect that that might be an ester. So how to make sure that it's an ester? If it's an ester, there will be one of those protons that is beside a CO. You will have a peak at 2 to 2.5. And you also have a proton that is beside a single bond O. And it gives you the reading at around 3.7 to 4.8. Let's look at the A levels one. So the same CO from ketone just now. So a proton that is beside C double bond O, and a proton that is directly on a carbon which is beside a single bond O, which gives you 3.2 to 4, which is around 4. Whichever board you take, it's still around 4 plus, which might mean that you'll see peaks here and here. Of course, whether it's a singlet, doublet, or triplet, or quartet, that will depend on its neighbors. So for example, if this is the side, the alcohol side of the ester, so if this is the case, you will get a quartet. 3 neighbors. You'll get a quartet at somewhere 4. So that's your clue. For example, I would suspect this is an ester. There is something at around 2 and 4. So it might be an ester. For example, this is 2 oxygen. There's something that is around 2 and something that is around 4. So this might be an ester.